So eigenvalues, eigenvectors. It sounds complicated, and it kind of is. So once again, this is the way to compute it. It's not the same as the definition. So keep in mind that why we're after eigenvalues, eigenvectors, because they are respectively the factor or the coefficient of the stretch and the vectors that are being actually stretched, because some of the vectors won't be stretched. Like if you stretch vertically, horizontally, it means that everything in between will not be stretched. So you have to decide where there is stretching in what directions, and then eigenvalue is the by how much. Okay, so that is very easy to see, and then we discovered an easier way to do it rather than going directly after that problem written at the top. There is a shortcut, and that is through the determinant of that matrix over here. This tricky matrix, which doesn't have a special name, but the determinant does have a name. It's called the characteristic polynomial. So this one. Characteristic polynomial of A. So once again, Eigen means characteristic in German. So that polynomial, you set it equal to 0, solve, and that gives you the eigenvalue. So you don't have to actually solve the whole problem simultaneously, finding both eigenvalues and eigenvectors. Okay, so that we tried it only once. Here's the example. I picked the very simple diagonal matrix, so that was no trouble to compute that thing, and you already immediately have your polynomial, which is a quadratic polynomial over lambda. Okay, so because A is fixed, it's given to you, filled with numbers, and then and lambda is the variable. Okay, so that is, well, actually there's a notation for it. It's chi sub A of lambda, the characteristic polynomial. So chi stands for characteristic. A is indicates as a subscript, indicates the matrix we're talking about, and lambda is the variable inside of parentheses. Quadratic polynomial, and that's where we ended up over here. That is our quadratic polynomial, the characteristic polynomial of the matrix A over here. We set it equal to 0 and solved it, and it was easy because it was already factored, and we found two roots of the polynomial, as it often is the case with quadratic polynomials, and those are the eigenvectors. I'm sorry, eigenvalues, and then we already have found eigenvalues, eigenvectors from eigenvalues. It's not hard. Okay, so I actually want to do an example that is slightly more complicated, and we'll be looking at the same thing. So that's a characteristic polynomial, and then finding its roots. So that's the method for finding eigenvalues, is setting up the characteristic polynomial and finding its roots. So we kind of made a full circle from abandoning everything that is not linear, and so stick with linear, but then we made a circle, and we're back to things we cannot really entirely avoid nonlinear things, and such as, for example, quadratic polynomial is one of them. And if a matrix is 3 by 3, the polynomial will be cubic, and on and on. So that is still to be discussed, you know, matrix n by n. So if you think about it, you just look at the matrix on the right. Okay, so this is an n by n matrix. Okay, so if you and I already drew in blue. In blue, I added this negative lambda over there, right? So there will be, as I said, when you compute the determinant of a matrix, there will be many multiplications, but one term is always present, and that's the diagonal one. So you multiply all the terms on the main diagonal, and that gives you one out of many terms in your determinant. So that term diagonal will always be present. Okay, so which means that, look at it, what it is. It actually lambda appears exactly n times. So because it's n by n matrix, n entries in the diagonal, so there will be n at the very least. The degree of the polynomial will be n if the matrix is n by n, and so you have to solve an nth degree polynomial equation. So even though we are talking about linear functions, this is definitely nonlinear. So let's, however, we'll, as far as computations by hand are concerned, we'll stick with lower dimensions. So here's one example. Then I want to work out my matrix. Okay, where is it? Here it is. My matrix is -1, -2, 1, and -4. Okay, so we don't know anything about this matrix, and we want to use eigenvalues, eigenvectors to actually find out something about it. Keep moving everything. Okay, so find. The ultimate goal is to find all three eigenvalues, eigenvectors, and eigenspaces. Okay, so step one is finding eigenvalues, and we form that matrix, we form the characteristic equation as the determinant of A minus lambda I, or I2, the 2 by 2 identity matrix, which is easy to form. You just write minus lambda on the main diagonal. So see what I'm doing here, like this, minus lambda. So it's the same matrix, 1 minus 2 minus 4, but then there is that extra term on the main diagonal. Okay. And then I am to compute the determinant. 2 by 2 determinants, not too hard. So it will be -1 minus lambda times -4 minus lambda minus 2 times 1. Okay? So just computing the determinant, subtracting two diagonal terms. Okay, so what do I have here? 1 plus 4 lambda plus lambda plus lambda squared plus 2. Okay, let's see, lambda squared plus 5 lambda plus 3. Plus 3. Hold on a second, it's not 3, is it? This is 4, right? That's better. Yeah, that's better. 4 for lambda squared. Okay, in 2. Okay, so it's lambda squared plus 5 lambda plus 6. Okay, set it equal to 0 and solve. So that's the next step. The next step is this, and solve. How do we solve quadratic equations? Quadratic formula. So won't try to be fancy, just plugging into quadratic formula. -5 plus or minus 5 squared minus 4 times 6 over 2 minus 5 plus or minus, what is it, 25 minus 24, right? Wait a minute, yeah, okay. Which works out nicely, and so by design, somebody designed this problem so everything would work out. Okay, so otherwise there is no reason for things to be nice. And so the numbers then are, what is it, 2 numbers as predicted. So it's -3 and -2. Okay, so before we find the eigenvalues, let's interpret this. So what's the interpretation of these 2 numbers? They're not zeros. So we found the eigenvalues, but what's the meaning of the eigenvalues, so that we can extract something useful from this.
The difference between it and the horizontal and vertical.
Well, the thing is, we don't know the eigenvectors yet. So I thought maybe before we find them, let's decide what is that we're going to do with them. So remember, what does it mean for -3 to be an eigenvalue? What does it mean? The word is the same. You should be looking for always is stretch shrink. Okay, so it means that in some direction, one vector direction, there is the operator, our operator A, works as a stretch by factor of 3. Minus 3 means what? Reverse, right. So in a particular direction that we haven't found yet, what operator does to that vector, it stretches by 3 and then flips it backwards. Okay, and then there are two vectors like that. The second one, however, is different thing is done with it. It is multiplication by 2 and then turn. So you can already imagine roughly how the vector behaves. So we don't know what those two vectors are, but we can imagine that there will be v1 vector here and v2 here. We don't know what they are, but we know what's going to happen under the under the operator A. It's going to do to it like this. So let me use some fancy colors here. So if this is v1 and this is this v1, v2, so v1 is multiplied by -3. So negative v1 like this, and the other one multiplied by 2, so like this. Oops. Multiplied by 2, so this is -2 v2. So that's what A does. So if this is still the origin, this is still the origin. Okay, so it's one plane on the left. The domain, the codomain plane is on the right, and that's what A does. So it does this disproportional stretching with a flip. So it preserves the orientation, by the way. So if you have a circle around the origin, it will be still going clockwise if it was clockwise, and so on. Okay, but generally there is a stretching in between these two vectors. It's not a stretch. It is a stretch, but also with a certain rotation. Okay, so that we already know what roughly that vector does. What's missing is we need to find those two vectors, those two particular vectors. That would complete the picture. Okay, so to find them, let's quickly write what we have. So I pick lambda equal to -3. What do I have? Then I go back. I have to write a v1. V1 is what we're looking for, is equal to -3 v1. So that's what we're supposed to find. That picture is right there. So v1 is stretched by negative. I'm sorry, I didn't put a 3 over here, did I? Like this. Okay. So that's what we are after. We have to solve this equation when for vector v1 when the lambda is known by now. So that's the advantage of this method, that lambda is known, and then I take my a, which is I'm writing the equation. We'll see how far we're going to take this -2, 1, and -4. I multiplied by the two unknowns. Suppose this is my v1, and it's equal to -3 xy. Okay, just even though we end up with the same equation as right here at the top, it is better just to at least once in a while remind yourself that that's what we're talking about. We're talking about this equation, finding what vectors are stretched by factor -3. Okay, so at that point you could convert this into what? Into an augmented matrix, right? So let's try it. So okay, so I'm gonna see, as you can see, there are no entries in the equation with no x and y. That is why when I move everything to the left hand side, I'm going to have zeros here. That's always the case. So okay, what are the four coefficients? Do we need to multiply this out? It's the same thing. It is a plus 3i v1 is equal to 0. So if you want to take a shortcut, this is what our equation turns into. So I bring that right hand side just the way we did it last time. I bring the right hand side part -3 v1 to the right, and factor v1 out. Okay, and that I end up with this equation, and the a plus 3i is our matrix. The matrix, not the matrix, the original matrix, which is the operator, but this one, the one that forms the characteristic equation, which we're now done with. But now we actually need to solve that system, and this is my augmented matrix. So what are the coefficients? negative 1 plus 3 is 2, right? So negative 1 plus 3, simply negative 2, 1, and here negative 4 plus 3, right?
Yes.
Okay, so in other words, it is 2, negative 2, 1, negative 1. So what do you notice about these two equations? Each row is an equation, right? So what do you notice about them?
Trying to figure out how you got to why you're adding 3.
You subtract 3, it was negative 3 on the right, so I bring it to the left-hand side.
Because it's lambda, okay.
Right. Yeah, so this is lambda. Lambda is negative 3, and so that equation is what we've been talking about a little bit.
Okay. Thank you.
Okay, so what look at the now our augmented matrix. What do we see there?
Y is reversed.
What?
Y is reversed.
Y is reversed? What do you mean?
Like, they're both negative.
Yeah, but no, look, there is a better observation to be made. Look at the two rows.
Same, like,
It's the same thing pretty much, right? So one is the multiple of the other, which means that we need only one of the two. Okay, so that is always happens when you do. You're not going to face the same as when we did early on. We're solving equations, system of equations. We typically would end up with one answer. That's not going to happen here because remember there's never one eigenvector. There's always at least a straight line of eigenvalues, so infinitely many answers every time. Okay, so in other words, what I end up with is x minus y is equal to 0, right? Or x is equal to y. So which means that I have a bunch of eigenvectors right away. So I certainly could pick v1 equal to 1, 1, right, as a basis. But then every multiple is also in the eigenspace. So I found so this is an eigenvector of lambda is negative 3. And secondly, I let me right away go straight ahead and pick the eigenspace. So the eigenspace is simply all of the multiples of this vector. So it is I don't know when I write what it is equal to. It is simply what is it? It is diagonal. The diagonal on the xy plane. The main diagonal, so this is it. So this is the eigenspace of negative 3, of our matrix negative 3. Okay, so once again, remember what it means. It means that this line is stretched by a factor of 3 with a flip. That's what our operator does to this line. The rest we don't know yet. So let's do the other one. So the second eigenvector is taken, eigenvalue is taken, which is negative 2, and we do the same thing. A v1 is equal to negative 2 v1 this time. Okay, so I'm not going to go through these things again. I go straight to the augmented matrix. So remember what it is. I take my matrix A, which is over there on the left, and subtract and add 2 to each to the diagonal terms. So it will be negative 1 plus 2 rather than plus 3. So these are the same. And negative 4 plus 2 again. Okay, so that is my my matrix, and so it adds up to negative, what is it, 1, negative 2, 1, negative 2. Even clearer, so once again we have redundancy. We have only one equation left, and we are solving it easily. So it is x minus 2y is equal to 0. Okay, so it means that x is equal to 2y. So I could pick v2 to be, what is the simplest one I can pick? Pick the simplest one. This vector will serve as the basis, sort of. 2, 1, right? 2, 1.
How would it be 2?
I choose y, 1, and x then 2, right?
But why is it 2, 1 and not 1, 2?
Because x is 2 and y is 1.
Oh, okay.
Right. Okay. So then is an eigenvector of lambda equal negative 2. Again, I attach a picture to indicate what my eigenspace is. So it is the line. What line? The line that we have, x is equal to 2y, is in fact an equation of a line, and that is the other eigenspace. So what is it? X equal to y is x over 2, so this is it. I can write it at y equal x over 2 just for convenience. Okay, so and that is line, and the eigenspace is e negative 2. Okay, so at that point we are pretty clear about what's happening. That picture that I started over here was I drew the eigenvectors randomly, but they are not that different from what we ended up with. They're very, very similar, in fact. And now we know what what A does. So what A does to the plane is stretches the line. Well, I can stretches the line y equal x by 3 and flips. Okay, so number 1, number 2 stretches the line y equal 1 x over 2 by 2 and flips. And then and now 3, what about the rest? And it's not as easy to describe, because remember that is the fanning idea. Fanning, you know, so there are two, think about a fan, not an electric fan, but actual fan, right? So it has two ends, and they are separate, right, like this, and then they're fixed. But in between, you could actually move these, whatever they're called, you can move them around, back and forth. So that's roughly what's happening. So you can, like, you're starting with so one and the other one. So that's my fan. Okay, and then there are the little paddles, or whatever you call them, in between, and they might be distributed non-uniformly, like this. So that's a fan. Best I can do. And that's, well, I didn't describe this as an operator, but really what's happening is this. Hold on a second, that's not it. Okay, so that's what it is. So you are holding a fan in your hand, okay, like this. And then, suppose initially those paddles or wings, or I don't know what they are, distributed uniformly. Okay, so the standard center situation, but it is some angle there, and then A transforms it. How? We already described that. So A does this. It stretches and flips, right? So the fan suddenly becomes large, if you can imagine that. So this is where we hold it. So it becomes larger, like this. So this, I multiply this by 3, and this one by 2, and both of them are flipped. So I flipped my fan, and I stretch non-uniformly, which makes those paddles also stretch and non-uniformly, and they will be bunching towards more tightly towards that longer one. Okay, and they will be more sparse here. Okay, so that's what A does. Okay, so once again, a fan that has well, it looks normal in the beginning, but then because of and then what you are, as a holder of the fan, you only control the ends, okay, and you flip them and stretch them, the ends of the fan, and whatever happened in between already is forced. It is just the nature of the fan that it happened. The fanning of those. Sometimes it's just made of paper, you know, like a fan made of a folded paper. You've seen it, right? So you just fold the paper, and you have your fan like improvised. So that you only control the two ends. So we have we realize then that's what the operator does. We could be more specific, and this is how. So A of V is equal to what? Fortunately, we can just express V as a linear combination of V1, V2. And that is the good thing, that V1, V2 are not multiples of each other, which means that they are together they force a basis, which means that every vector on the plane can be expressed as a linear combination of v1, v2. Okay, like this, alpha v1 plus beta v2. Okay, so now if I apply the operator A to it, what is A of v? What is A of v equal to? There may be. So can you just tell me what this is? So remember, how do you compute a linear operator of a linear combination? Remember, what is it equal to? That's right. So remember, linear operators, that's their property. That's why they're called linear, because that's how they handle linear combinations. You break it. You take those alphas outside, like this. So it will be alpha A of v1 plus beta A of v2. Okay? But we know what these are, so that's why we're doing this, because these two are known. These are our eigenvectors, or rather bases of our basis elements of our eigenspaces. So we have them right. We know that they are being stretched, so it will be alpha negative 3v1 plus beta negative 2v2. Okay, so as you can see, if you know what are the coefficients of that linear combination, then you don't need to do anything else. You know the answer where that vector, any vector v on the plane, will go. That's where it goes. It goes to a linear combination of those two, which is pretty much what this picture is. So let me try to illustrate that. So if I have a v here somewhere, oops, then what happens to it under A? And it's also a linear combination of the result. So if this is v1, which one is v1? This is v1, this is v2, this is negative 2v2, and this is negative 3v1. Okay, so and then my v is here somewhere, like this. So hypothetically, if my v was say halfway, well, it's not gonna remain. If it was halfway between v1 and v2, it does not mean that it will remain halfway between a of v1 and a with v2, because of this fanning effect. But otherwise, it can be computed, and that's we know the answer right away. It is a rule of linear algebra that linear operators are easy. You don't need to know every value. All you need to know is its values on your basis. So if your basis is made of only two elements, then those are the only two values you need to know. If it is a high dimensional space, n dimensional space, you need n values of those basis. The point of this analysis was actually to find the best basis that makes A easy. Okay, so once again, the A is initially written with respect to the standard basis, that one, the standard Euclidean basis. Okay, but it's supposed to work for every linear operator, which is certainly not the case. Turns out we can find a better basis for this linear operator, which, with respect to which things are very simple, and we found it through this analysis, and that vector is made of the two eigenvectors. Okay, so what does it mean? And that is the part of a bigger topic. But A, well, let me put it this way. This is how we can describe the outcome. The matrix of the operator A with respect to the new basis, which is v1, v2, is diagonal. So it is simply negative 3, 0, 0, negative 2. Okay, so in every basis, you have a linear operator. Whatever basis you pick, you can find a matrix for it. Some of those choices of bases are better than others, and in this particular case, the ideal basis for a linear operator is the one that consists of its linearly independent eigenvectors, and it worked out for this particular linear operator, and we found v1, v2 specifically they are pointed out here. So if I could repeat that again, so there's here somewhere v1, and there's here somewhere v2, okay, and then we choose them as our new basis. So the basis would look like this, literally like that. Okay, so that's my basis, a new basis. And with respect to that basis, look, it looks like a basis, and except it's not perpendicular, but we don't care because we don't do any dot products, we don't do any distances. So the fact that we don't need the basis vectors to be perpendicular. Okay, so all we do is linear operations. We do linear combinations, and any basis is just as good as any other. And it turns out, yes, we have a new basis, and it is really a nice one. Okay, so that is the goal of this kind of analysis of eigenvectors, eigenvalues, eigenvectors, eigenspaces. Okay, you can imagine that things become complicated once you go to high dimensions. And now I want to decide if I want to deal with the high dimensions, or that's actually not the hardest part. I'll probably have to do a little bit of both. So let me, well, just to make it a little illustration. So let's illustrate what we just did with Excel. So this one is fanning. Let's see a fan that is more specific. I did everything by hand, so let's do it with Excel. So can you quickly read to me the entries for my matrix A? Is it 1? Negative 1? Negative 4.
The first one I thought was -4.
Where is it? I lost it. So negative 1, negative 2. Okay, negative 1, negative. Where is it? Negative 1, negative 2, 1, and negative 4. Okay. Okay. So so you can see what has happened. So the spreadsheet doesn't do the analysis that we did. It only determined the eigenvalues, and as you can see, eigenvalues are negative 3, negative 2. So that our computation was correct, but it does not find, and not in this one, it does not find an eigen vectors here. So let's just make sure that you can see the fanning effect. So not only they are spread out somewhat, but they are also flipped. Okay. If we want to see eigenvalues, eigenvectors rather, and eigenspaces, this is the other one. I'm not sure which one is the better. Let's take this one. Eigenspaces. Okay. So once again, negative 1, negative 1, negative 2, negative 2, 1, and negative 4. Right. Okay. Here it is. So these are the two eigenspaces, right? The red and the green. The red one is, which one is the first? The first one. The green one is the diagonal. That's the first one, and the red one is the second one. Okay. So that is the analysis, just the analysis, and then you see the effect of the operator on the right. What has happened to those circles, concentric circles? They have become ellipses, even though it would be very hard if you think about it. They certainly do look like ellipses, but it's not really clear in which direction that ellipse is pointing. Look at it. It's not pointing along any one of the two eigenvectors. No, it points. I'm not even sure in which direction it points. I think it points to the right. It roughly 2, 1 or something. 1, 2. It's roughly that's where it is pointing. So doesn't matter. That would take a different analysis. Let's just say there is a stretching, simultaneous stretching disproportionally in these two directions. and flips. That is why, because of the flips, you can see that the circles that go counterclockwise are still counterclockwise. They are now ellipses, but the direction is the same. So that we say that the orientation is preserved. Okay, so there we go. So that's roughly what the analysis tells us. In the n-dimensional case, what happens in the n-dimensional case? So that is a little bit of algebra comes into play. And so facts such as, so if A is n by n, then the characteristic equation is an nth degree polynomial. And now what is important here for us, and that so the eigenvalues are its roots. Okay, so so we're done with this example. And now we see the complexity of things. So solving equation of nth degree is hard to do by hand. It is impossible to do by hand, as a matter of fact. So you may have heard that polynomials of degree 5 or higher do not have a formula. We have quadratic formula, we have cubic formula. We even have a formula for the polynomial of degree 4, but not 5 and beyond. So there is no formula. It's not because we cannot find it, because there isn't any. Okay, which means that generally speaking, you have to apply computer inevitably to actually generally to pick up any matrix and find its eigenvalues.